once we get closer, we'll talk about what things are on there. Okay, last time we talked about Huckel theory and semi-empirical Huckel theory. Why are we talking about these things in this class? Yeah, so we can look at energies and we can look at electronic structure. So have you ever been in like a Gen Chem class or like a talk and it's like, okay, well, here are the orbitals and they overlap, and oh yeah, by the way, there's S and P mixing, so this orbital up here, they're actually a bit lower. And you get really irritated because there seems to be no rhyme or reason to what's going on. The reason for that is the person talking to you in front of you has experience with this, but the spot that you really truly get it from is quantum chemistry. That's where those MO diagrams come from, where you can understand what's actually happening in a system based upon some of these fancy pictures. They also have forms of spectroscopy to help you out and understand that too. But the whole point is to be able to calculate the electronic structure. Where are those electrons going? That's the whole point of what we're trying to do here. Because one, we can understand systems better by knowing what that electronic structure is. Also, we're talking about electron density maps with our crystallography, right? That's based completely off of the electronic structure. So we talked about extended Huckel theory and Huckel theory because we're going to use those a lot. But what's used today in practice? DFT is, and that's what we're going to talk about. We have other theoretical methods, but if you talk to physicists and solid state chemists and most computational chemists, the one that they tend to go with is known as density functional theory. If you're interested in other theoretical methods, we talk about them in PChem too. Shortened to DFT. DFT is selected because it scales n to the third, where n is the number of our basis functions. And that tends to be one of the fastest computationally to evaluate. The other thing is it generally gets a good answer. The quality depends on the functional you select, which we'll talk about what that means in a little bit. The other cool thing is in theory, you can get an exact answer. There's something out there called the universal functional, that there's a proof for it, that it exists, and it gets the exact answer. You know the electron density, you know the wave function, you have everything. The problem is that proof just tells us it exists. It tells us nothing about how to get there. And people research really, really hard on how to get there. Do you think we have the universal functional yet? No, if we did, you guys wouldn't be doing any experiments. You'd just be calculating stuff all the time because you would get the right answer every single time. Then we would do some experiments after confirming some stuff and seeing what we can make money off of. Or make into a weapon, one or the other. It depends on what you're getting funded by. Okay, so, and it scales relatively fast. So do you guys know what this like end of the third means or not really? Okay, so this is related to, it's proportional to the computing time or computational expense. That's a relatively low computational expense. So what it means is for every basis function I have, you're looking at like the time according to it, it goes to the third. There are other theories out there, like Hartree-Fock theory. The scale's end of the fourth. What is it? MP2 scales anywhere from end of the fifth to end of the seventh. So these other theoretical methods take way longer, and they generally give a worse answer. There are some that do incredibly well. That scale end to the seventh, ninth, or higher, such as configuration interaction or coupled cluster. Those calculations, though, can take months for even simple systems. So I remember when I was in grad school, we had a guy who came to talk, and he talked about N2 and how they had the exact solution for N2. And they were super excited, and it was an hour and a half long talk. And I was like, we're talking about N2 here. It's 2013. What do we do? We're still talking about this? And we did. And it was exciting. It just takes a really long time. That can actually do better than experiment will ever achieve. It's cool to think about too. Okay. So let's talk about DFT, what it relates to. Density functional theory operates differently than a lot of the other things we've seen. So far, we focused on getting a wave function. What DFT focuses on is getting a wave function and getting an electron density and getting the wave function from that density. So the electron density. And everybody gets what I mean by electron density, right? Does anybody not feel confident or does not feel like they could explain what electron density is? Okay, can you describe it to me? I want more words. Like, what is it related to? Yeah. It is the probability you'll find an electron in the region of space. You don't want to add orbitals in there, though. That's an okay way to talk about it when you're first introducing it, but you don't. The guy that we're going to see at dinner tonight, don't open with that one, or you're going to have a long rant at you in German. Oh. No, it's okay. It's entertaining. For you. It is for me. I got him really mad once because I said he can come, like, this is America. I was talking about ammunition or whatever, and I was just completely messing with him. Got very mad at me. And then he was in my thesis defense. That wasn't smart. Don't do that. Also, don't drink before your thesis defense. That's another thing, too.
Wait, how did it go so wrong? It didn't go wrong.
What was that?
It didn't go wrong.
No, I got questioned for 3 hours or so. Just a long. If you say you're going to go into academia, they just hammer you for a long period of time. I got to the point where they were just like, yep, that's okay. I'm done. And I went, all right, can I go home now? And I drank snake wine. It was delicious. My friends in the Philippines, what you do to prove you're a man. You have a bottle, you put a cobra in it.
Like it's snake wine.
Yep, it's called snake wine. I use my cobra. And they fill it with vodka. Cap it. Then you drink it to prove you're a man. I became a man that day. Thanks, Irwin. It was horrible. It was the worst tasting thing I've ever drank. All right. So we can get the electron density. Taking the complex conjugate R, we're telling where our electrons are. It's a vector quantity, and we do this. Nothing new there. We talked about it earlier in this class. We beat it to death in PChem. We know the energy can be found. How do we find an energy, or have we done it so far in this class? Yep. Hamiltonian, it acts upon our wave function, which is a function of the coordinates of the electrons. What do we get out the other side? Mm-hmm. Yep, eigenfunction. Okay.
Is it specifically a dot product, or is it just?
It's just multiplied. I'll leave it like that. I don't want to talk about dots and crosses right now. Okay. So now, this is wave function based. Density functional theory is all about looking at the electron density, trying to figure things out. So my question is can we use the electron density to get an energy? So what do you think? Can we use that to get an energy? Yeah, that's why we're talking about it right now. Yes. Exclamation point to show our excitement. That's what DFT does. So in DFT, E naught, what did we say E naught was again when we were talking about the variational principle? Yep, the ground state energy. So that's the energy of the lowest energetic state we can find. It's actually a functional of the electron density. So the energy is a functional of the electron density. I use the term functional. In your math courses, have you guys talked about what a functional is? Probably. Okay. I don't recall in my undergrad ever discussing what a functional was, but that could have just been me. I also learned all of my mathematics from physicists. I didn't learn any of my math from mathematicians, except Dr. Cox. He was awesome. Dr. Chekla got me through Calc 1 when I was a horrible student, so I thank him. Nothing like just getting a C me rather than a grade on an exam. Oh yeah, I got one of those. Did I ever tell you guys that story? Okay. I was up in Buffalo at a Cannibal Corpse concert. Does anybody know who Cannibal Corpse is? Okay. If you ever watch Ace Ventura: Pet Detective, they're the guys who are like, whoa, when they go into the basement in that one area. I was in there. I went into the mosh pit. I weighed about 20 pounds less than I do now, so I was about 130 pounds. Just got beat up. I slipped. I hit my arm. I had this lump on my arm. I couldn't write with my right hand, so I had to write with my left hand. I had been up more than 36 hours at that point, was taking my the second Calc 2 exam, and that's how it went. And that's when I changed my life around and became a better student. Yeah, I did not start as a good student. I only cared about my chem classes. That was my problem. All right, so let's ask the question, what's a functional? Okay, before we do that, let's remind ourselves what is a function. Okay. Functions associate a number for which the function is defined. So as an example, if f of x is equal to 2x plus 2, what's f of 2? Yep, it'll be 6. We just plug in that number and we evaluate. Gets us a 6. Okay. A function is often said, or functional is often said to be a function of a function. So as an example, we'll have a functional capital F acting on a function f of x. Have you seen something like that or no? Okay.
Yeah, none or teams? Yeah. Oh, yeah. I'll figure it out.
Dx. So in this case, we have a functional acting on our function f of x, and this is the operation. It's one that I just defined. That's a complex conjugate. Okay. We could replace f of x with what symbol? Yeah. We could put in size here, and it's the same thing. You've actually been using functionals but haven't known it in the past. Okay. So that's what a functional is. We know that we have some energy functional that operates on the density and spits out the energy that we're interested in. Well, let's talk about how does this actually work in DFT. So returning to DFT. How does this work? We're going to do something kind of crazy that you will think there's no way in hell that that will work. And then it works. It is amazing that it works. We don't want to solve a system where all the electrons interfere with one another. Right? Because we run into that many body problem. What could we do instead to make... Yeah. It would be way easier to solve a system where the electrons don't even see each other. Right? Okay. So like when they were developing this, computers weren't really great. Let's take a first stab at it. Let's see what happens. It would be easier. I'm going to switch to the big chalk. My handwriting's getting worse. Oh, there we go. To solve a system if the Hamiltonians were for non-interacting. A non-interacting system of electrons. Then our Hamiltonian could be expressed as a one-electron Hamiltonian. The other benefit is we wouldn't have to worry about that many body problem or any of that other junk. And you're probably thinking there's no way that this will work.
I know.
It will, yeah. There's a proof out there that it's one of the tenets of DFT, where we assume we have a fictitious system, which I have to stare at this and hope I spelled fictitious correctly. That does not look right at all.
First U is right.
First U?
Oh, wait, no, there's two.
Yep, there we go. We did it.
Good enough.
Non-interacting electrons. So we have this fictitious system of non-interacting electrons that has the same electron density of a real system with electrons that do interact. Okay, so what we're saying is let's pretend we have an H2 atom. That's a real density. We build a model. And we construct that model so the density that we predict is this. Are those densities different? No, they're the same. So we make up a system, we say the densities are the exact, we match it, and it works.
So do you determine those experimentally, or is it
You can.
like how you're getting the densities to begin with?
Electron density maps, ellipsoids, all of that stuff. These densities are the same. So that means we make a fictitious system where the electrons don't interact, and we minimize that energy, and it should match one where the electrons do interact. And then they're the same. There's a proof associated with it. There's one that's way more complex, mathematically complex, that I don't want to tackle here. But if you're really interested, I'll give you some reading associated with it. Okay. So we have this fictitious system. We have a real system. Then how do we actually calculate the energy? Okay. We have our energy that is a functional of what? Or excuse me. How are we going to get our energy out? I guess I should have asked. We're going to use a functional, and what's the functional going to operate on? We want to use electron density because we've made a fictitious system, yada, yada. Okay, now let's break our energies up. Just sort of like we did with the Hamiltonian. We're going to have a different functional for different contributions to that energy. What are the two types of energy that we have? Potential and kinetic. Okay. So in this case, we're going to deal really with just more of like the electronic version of this system. what are we going to need terms for?
Nucleus and the electrons interaction.
Mm-hmm. So
What's up with this one?
I want to start with a different one, but we'll go there. So this is the nucleus-electron interaction. It's a function of the electron density, our fictitious electron density. What else do we have? Yep, we got kinetic energy of the electrons. I would wait to write everything down until we get everything up there. Okay? Now, T, I don't really know why. I've always hated that, but it is T. This is for our fictitious system of the electrons not interacting or seeing one another. If we want to make it more realistic, what do we got to add in here? Yeah, we got to add a correction term. So we're going to add a delta T for a correction left behind from physics of the kinetic energy because, you know, the electrons will see one another and they'll repel. We'll throw it into a fudge factory.
What is an operator assumption that they don't see each other?
Oh, like how doesn't it? Well, we can just sort of split it up that way, and we're going to throw in all the stuff that doesn't make our assumption true into this other term, which we'll talk about the other term in a minute. Okay?
So is that term not a part of that term?
This term is separate from this guy. This is for the non-interacting gas of electrons. Okay. We're going to leave the nuclei out because we're just looking at the electronic energy. But yeah, we would include the two nuclei. We'd do a Born-Oppenheimer approximation, and then we'd get rid of those things. But we're kind of just being lazy here. We have another term. In this case, we're going to include a classical term for the electrons seeing each other. So just the pair of one electron with the other. Is that completely true? Nope, we got to add in another correction term with that potential. Okay, so let's go through and label what these things are again. This thing, it's the kinetic energy of what? Nope. This is for the kinetic energy of the non-interacting electrons. Where'd my yellow go? I'll just use this crappy yellow. Sometimes. This guy, what's this thing? Oh, I'm switching, can't do it. Yep, nucleus electron interaction. I'm going to switch to green. This is the classical electron-electron repulsion. This thing, what is it? Yep, it's a correction term. To what? Yep, specifically what type of energy? Yep. Due to non-interaction And then that last term, what's that thing? Yep. To electron-electron interaction. So this is classical. Do electrons behave classically? Point charges? No. This portion here, this allows us to include quantum mechanics kind of in that portion. Okay. I don't know if you guys enjoy this as much as me. I see a lot of groaning.
It's just because today, like, after
No.
You should-
For me, I think it's cool.
You should be energized after break. What's going on? Yeah.
You had a short taste of freedom.
Yeah. Never give them freedom.
I also have like a migraine.
Oh, so staring at a bunch of stuff helps out a lot. You want the bright lights probably don't help.
Yeah, I was wondering if you could actually increase
Yeah. My kids always have this dumb goose toy that likes to come out when I have a migraine that just is the most annoying thing ever. I know my younger brother bought it for them because he's a bastard. And it just comes out. Oh, it is. I am going to do, I've got a bunch of toys for him when he has kids. Gotta be great. Revenge.
Just give it back. Save them in a trunk and give it back.
Mm-hmm. Combine them into one noisy thing. Get them a drum set. That'd be the death knell of a parent's brain. Okay, so now we got a bunch of these energy terms. Which ones can be solved for exactly? Yep. Yep, what else? Yep. Then one more. Yeah. Yeah, you guys do that or did it a million times, and probably physics too. With
Oh, yeah.
point charges. Yeah, Coulomb's law.
Oh, the Japanese class.
Mm-hmm. What about the others?
Well, we're able to solve only one of the
Yep, the mathematical proof. This is what it does. We're going to lump them all together and worry about it later. So, our energy functional becomes this, where we have that non-interacting kinetic energy term, the nuclear electron attraction, the classical electron-electron interaction, and then we lump those correction terms into this other thing. That's meant to be an X. This is what is called the exchange correlation energy. For electronic exchange, there's no classical analog to it, but there's basically a penalty for when you can distinguish electrons apart from one another. Correlation we've talked about in the past with the many body problem where each electron interferes with the other one. This is kind of a misnomer to call this the exchange correlation energy because what else have we lumped in there? Not just these electron-electron terms, which really have to deal with the correlation energy. What other thing do we have kind of tossed in there? Yeah, we have the correction to the kinetic energy that gets thrown in there too. So next time, what we're going to do is we're going to talk about how did this actually help us? And then we're going to discuss how is this term calculated?